So today we're gonna go over chapter 6 and 8. Okay? 6 and 8. Agreed? Any question about what I talked about last week? No? You'll have to do 6 transition graph, and then you does 6 and 8. Mealy machine, Moore machine. Those two will do that. Basically, last week we talked about two important language concepts. They are regular expression and finite terminal. Regular expression, finite terminal, right? So basically, regular expression and finite terminal, they are basically the same in terms of representation. They are the same. The regular expression basically allows you to define the language as like a set oriented notation. That's why we used recursive definition to define regular expression, right? And we looked at different kinds of regular expressions and various types. And then we turned to finite terminal, where you actually use a finite state machine to model the language in the same fashion as we did with the regular expression. But the difference is finite terminal is finite state machine. Number of states are finite. And then you can basically model the language concept through the sequence of transitions. You know, it allows you to move from state to state, and then basically there's a route that leads you to the final state. When certain strings reaches to the final state, at that point you know that the machine accepts it. Every string that does not end up in final state, the machine does not accept. So only when machine reaches to the final state can you confirm the string is accepted. So that's basically how it works. Now today I'm going to talk about transition graph, which looks like finite terminal. As you can see, so transition graph looks like finite terminal. But there's some difference. Okay? The difference is, by the way, by looking at this picture right here, can you see any immediate difference between finite terminal and transition graph?
It's unidirectional.
It is?
Unidirectional.
Unidirectional. The finite terminal is not unidirectional?
It's bidirectional.
What do you mean bidirectional? Bidirectional means you have two arrows in one line. Unidirectional,
It's just one.
one is unidirectional, but bidirectional. But did you allow two ways in finite terminal? What do you mean?
Two inputs are
We have one.
No, I mean finite terminal. It looks like finite terminal, except one. In other words, finite terminal also one directional.
Yes.
You can go this way, come back. No, not just unidirectional means one way, but what I'm saying bidirectional, same line, the two arrows. That's bidirectional. But you can go this way and that way. That's not that's unidirectional too. With two different routes, from Dallas to Greenville, Greenville to Dallas. The two, unidirectional, or two ways. Maybe I don't know. You may call it duplex or something. But anyway, good point. Anyway, but we can put this way too. Let me well, it's coming this way, it's going this way, and so there are 1, 2, 3, 4 incoming edges, and then 1 outgoing edges. Okay, so there are two outgoing and 1 is incoming. Anything else you find? Okay, the directional constraint is fine too. But what else can you see? Multiple? What do you mean multiple elements? For example? Yeah, it's in other words, string, more than one symbol. Every time final terminal, to move from one state to another, you move in response to single string. But in this case, there's more than one symbols for transition, right? So in other words, the string is allowed. That's the main difference. Final terminal only one. Only one symbol. You know that, right? Final terminal only one symbol on a transition, but in this case, this is fine, these are fine. Right here. Instead of A or B, it had AD, BA, AA, B. You see that? Or it can have ABA. So in other words, transition can be defined in response to string, not only symbol. You know? So that's the main difference. So with that notice, we can go and look at definition of transition graph right here. Transition graph is a collection of three things. First of all, a finite set of state. Finite set of state, very similar to the finite atomic, right? Finite set of state. One of them start and the sum maybe non-finite state. What's the difference between this and the finite atomic? Do you see any difference in terms of definition? Same. Finite automata, finite number of state, right? For the transition graph, finite number of states, same. Well, that's just, you see a difference. How many start state in the finite automata? How many? Exactly one. Here, how many? So, how many can you have? More than one? Can you? So there's a difference, right? Finite automata, you have only exactly one start state, but transition graph, you can have one or more. That's the difference. Okay? That's the difference. And then number of finite state, maybe none or some. So what's the difference? Zero or more. How about finite atomic? Same, zero or more. So there's no difference in terms of finite number of state. The only difference here is start state. More than, it could be more than one. Okay? Or could be zero. Although it doesn't make any sense. It be zero. Number two, sigma, alphabet, sigma possible input letters. The same, right? Sigma, set, number O, alphabet, set. Number three, finite set of transitions. You have transitions in finite automata, and you have transitions in transition graph. No problem. Now here's how we specify how transition works. Show how to go from some state to some others based on reading specified substring of input letters, even the null strings. What's the difference? What's the difference between finite automata and the transition graph? Almost same, but there's one difference. Almost same, but there's only one difference that you should notice. The difference is?
Substrings, it contains substrings.
Yes, substrings instead of letter. Finite automata, it says, in response to letter. So in the transition, you have only one letter in the finite automata, but transition graph, you can have string, substring, right? So more than one strings, more than one symbols can be used to move from one state to another. Transition. Okay? So, let me summarize. Transition graph is same as finite automata with this difference. Number one, transition graph can have multiple states, start state, maybe none as well. Okay? Transition graph defines a transition based on substrings. Yes. More than a symbol, right? Substrings. That's two differences. Main, other than that, transition graph, finite automata, the same. Okay? So that's the difference. Okay? So now we go to some example transition graph. May I? So this is tension graph. Safely, like we can say this is tension graph because of substring AA, substring BB, right? Everything else looks like on the camera, right? Now, looking at this, what can you tell about the language defined by this tension graph? The language defined by this tension graph. Can you understand what language defined by this?
Star into AA plus BB, A plus B star.
A plus B star.
BB, AA plus BB,
AA plus BB and A plus B star. So that's very good. That's regular expression. So language will be English addition. All words will end this with double A or double A. Yeah, double A, double D's. Don't you think it's easier to understand than Panatamara? Do you remember we had Panatamara for this? Tension graph is much easier. You look at it, immediately understood, right? There's two. You have to go, you need to have double A or double D. See, that's the advantage. Advantage of having tension graph. When you look at it, you can easily understand. Another advantage is easy to build machine to define all modular HMBs with double A's or D's. Okay? One possible problem I see here is, one potential problem, however, is that when you do this now, when you have B here, do you need to stay or do you need to move? When you have B, I have single B. Let me do this. How about I have a triple B's? So for example, there are some potential consequences that arise from this. When you have triple B, how can you trace this? Triple B. So first B, right? So you really want B, first B here. Then what do I do? Do I move or do I stay? Do I move or do I stay? Move? Move? Move. Stay. So, stay or move? More people will stay. How about next week then? If you stay? What do you do? Stay and move? You can do either way, right? You can do either way. It's can't move because it doesn't say. So I can stay B, 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 right? Accepted, not accepted? Not accepted, right? But I can move. If I move, I take two B's, right? Two B's and then B's. Accept or not accept? Accept. So depending on how you move, either it may accept or may not accept. Okay? So one problem with the tension graph is it basically we call it non-deterministic. In other words, it does not, at one point, there are more than one ways. Okay? If you have more than one ways to move, it's non-deterministic in nature. Does that make sense? So the grammar, if the grammar parser machine has non-deterministic nature, you have a significant problem. It's like, you parse your program, in the morning, you have error message. Okay? But next time when you run it in the afternoon, you don't have error message. First time, it didn't accept. The second time, it accepted. So that is not the property you like to see on grammars, right? So, but it's good machine and it helps us to formalize a special case of a special case of languages, but the one non-deterministic nature is a potential problem that is in this tension graph. But it's good formalism that make us to understand certain language easily. Okay, so let's take a look at other examples. But that's non-deterministic. When you have, what I'm saying, when you have, when you let's say I'm here. One, two, three. For example, when you have a case like this, from state one, if you have B, you can always stay. If you have A, two different ways, right? That is what called non-deterministic. Non-deterministic. Okay? If you have only one way, then there's no case of more than two. Then we call it deterministic. So when you say finite automata, by definition we mean deterministic. When it's non-deterministic, we say non-deterministic. Yes, let me take a look at another example here. This one, that example shows that when you start from here, and there are two routes that lead you to a final state. This route, upper branch or lower branch, right? Both branch defines a string BAA B. String BAA B, right? So it says BAA B. In two different ways. Non-deterministic. Now, let's say this is, let's say it's tension graph. Why is tension graph? Let me ask you this, is it finite automata? By definition, it is finite automata? It is? Finite automata. With one symbol, right? Then can you say that this is a tension graph? Can we? Can I say this? Let me ask you this. Is it all tension graph is finite automata? No. You have string, right? Are all finite automata tension graph? Yes. It includes substring, includes symbol, right? So if it's finite automata, still I can call it tension graph. But I cannot call every tension graph a finite automata. Now, this is finite automata, also tension graph. Okay? What do you think this will accept? Can you easily see the language accepted by this? Looking at this way, the two ways to go to final state. Either this way and that way. What language do you think it is accepted? English what? You define English? All strings of alien is?
Starts with A and ends with B.
Or?
Starts with B and ends with A.
So now the first letter, last letters, different. See? Easy to see. Tension graph, right? Start with A and B. Start with B and B. So first letter, last letter, different. You know the regular expression, right? A, or strings, B, or B, or strings, A. That's how it works. What else can you see from here? Anything else you notice? In terms of this concept I wrote. What else? Is this deterministic machine or non-deterministic machine? Deterministic? Deterministic? Non-deterministic or deterministic?
Deterministic.
I'm asking you whether deterministic or not deterministic. Ask me again.
It has two different ways, right?
Okay, let me ask you this. From this state to here, if you B, do you want to move or stay? Move or stay? Move. Can you stay? Yes. Can you move?
Yes.
Deterministic, non-deterministic? Non-deterministic. Okay? So when I ask 2 times, 3 times, 10 minutes, there's some reason for it. So this machine is non-deterministic because when you have A, you can state or move. So if there is more than any one state has more than one edge to do, we call the machine non-deterministic. Make sense? So it's non-deterministic final automata. The final automata we call it FA, but non-deterministic final automata. Normally I write NFA. Non-deterministic finite automata. Non-deterministic finite automata. Okay, so you can come up with a regular expression for this, right? But oftentimes, that's the test, midterm test, for example. We given final automata, I ask you to build regular expression, right? That's what you get a question to look like. Given the final automata, you build regular expression. So practice means all those exercise problems, example problems, you try to convert final automata into regular expression. Okay? Or English definition as well. Given English definition, can you build a final automata, So that requires some practice, and the book has a number of examples and exercise problems. So how about this? The bottom one. So this bottom one here, transition graph, yes. Final automata, it's not final automata because of transition graph, right? So please look at this and see if you can define the language. Either in English or in English, in regular expression. Either English or regular expression.
Even number of ways and even number of keys.
Even number of A's, even number of B's,
When we go from
or odd.
and starts with A and ends with A. From first to no.
BAA?
No.
BAA?
Ends with the
Even number of A's and B's.
So A's must be even. You call it even clumps, right? Even groups. Not even number. Even number means A, B, B, A is even number too. But it's like even cluster, even, consecutive even. 2 A's together, 4 A's, 6 A's together. Not A, B, A, B, A, B, A, B. Like that's even numbers, but they're not together. If they're not together, that's not accepted. There has to be, A's must appear as even clumps. 2 A's together, 4 A's together, 6 A's together, 8, 12, even numbers. Whenever A appears, it has to be even. Okay? Now, next. How about other constraints?
At least 3 B's.
At least
3 B's.
3 B's what? Where?
Inside 2 B at least.
2 or 3? 3. Yeah. The ending has to be 3 or more. Ending must be 1, 2, 3, or 4, 5, 6, 7, 8, 9. So ending must be 3 or more bits. Okay? 3 or more bits. Make sense? So what is your regular expression for this?
A star B B B. A star B B B.
Yes.
You can have B's also, as many B's as you want to. A, B, B, B. This part is repeated. Not just A star. Right? Not just A star. In other words, combination of double A's and double A's and double A's, double A's and single B's. Double A, single B's. That part. This part is combination of double A, single B. Make sense? And then at the end, you want to make sure that 3. is will actually will be added there. So AA, B, whole thing, and then BBB. Okay? So that's transition graph. Oh, how about this? What about this one right here? So that's definitely the transition graph, right? Definitely transition graph. And what about the language defined by this? Any idea?
Starts with A or
Number of A's and B's? Number of A's and B's
Even.
are even?
Yes. ABBA. Sorry, ABBA, we can say number of A's and B's.
Yeah.
are even.
Even numbers, because if you have ABBA, you have the ABBA to go back. Any number, even number of A's, even number of B's. So in the regular expression, we have even, right? Final terminal, how many state? Oh, with the even. Remember, last one we did. Chapter 5. How many state? 4 states. Transition graph, how many state? 2. Simpler, easier to understand than final terminal. So however, this defines even number of A's, even number of B's. Okay? Even here. No, this. So now, this case, transition graph, from 3 to 4 and 3 to 5. What does this represent? Non-deterministic. Non-deterministic. Because you have 2 A's with same string, right? If you have ABB, you can go this way or that way. Non-deterministic, right? That's what we call non-determinism. That's not a good property, but you should understand what non-determinism is. So non-determinism. That's it. So problem, I'd like you to do is problem at the end of the chapter. Problem number 2, number 3, 4, 5, 6, 7. Okay? 3.
2, 3, 4, 5, 6, 7.
Did I say 3, 2, 4, 5, 6, 7? Okay? And now we do regular Moore machine, Mealy machine, chapter 8. Okay, I have one question here. The question is, what is the input and output, input to the final terminal and output from the final terminal? What's input? So let's think that way. What is it? What was it? Okay, what is input to the machine, final terminal machine, and what comes out of it? String is input. So you guys take string, right? Take string, A B A B A. You feed that string to the final terminal. So what do you get at the end?
Regular expression.
That's the final terminal. What final terminal produce? What do you get from final?
if it's acceptable or not.
It is either yes or no. That's it. The output from final terminal is whether the machine, the language string is accepted or not. So you get one of 2 answers, plus a yes or no, right? That's the output. In other words, what you give to the final terminal is you give A, B, A, B, A. Generally, my expectation would be another string like that, but rather than a string, the final terminal will give you final automata will say either accepted or rejected. Okay? It's yes or no. That's the output. Okay? The output is final automata says you accepted, not rejected. Transition graph, same thing. Because when you end up in a final state, it's accepted. When you don't end up in final state, it is not accepted. However, now there are cases when you want, based on function AB, AA, if you want, instead of accept, not accept, yes or no, if you like to have the final automata, if it's A, I want to make a B. If it's B, A, B, A, B, something like this, some kind of output string. So input string is given. If you like to have output, string and an output, different machines need, right? But this chapter, there are two machines that does it. Two machines that do produce strings. The one is Mealy machine, and Moore machine. Okay? So that's like final automata, but the thing is, the question is, when you have final automata, when you have final automata, say for example, when you have final automata like this, state number 2 and 3, and you have A, transition like this. When you have final automata like this, if you are to specify output, where do you think you specify? Somehow you have to specify, right? Previously, final automata accepted means you reach a final state accepted. If you reach non-final state, not accepted. That's clear, okay? 1 or 2. Now, however, in response to every single letter in the string, you are to produce a letter as an output. Where do you think you need to produce? Where? That's the question. Where? If you have to produce output, you have to specify every single, in response to every single letter, you have to produce an output. So in response to every single letter means, where does every single letter appear? Where? On transition, right? On transition it appears. So what I can do, on transition I can always specify like this. Slash. Slash, what comes after slash is what's to be output. Make sense? So every single time, every single transition you specify output letters. Okay? If that's the case, we call, in this case, we say is Mealy machine. Okay? But there are other cases also. Where do you think? Okay, let's make a guess. Now, if not transition, where do you think we can produce output?
Within the state.
Yes. If it's not a transition, it'll be state. Okay? Maybe A or B like this. So if that's the case, if you produce output in the state, we call it Moore machine. You see the difference? They are the same machine that are same. The two machines are the same. One machine produces output in the state, the other one produces output in the transition. If you produce output in the state, we call it Moore machine. If you produce output on transition, we call it Mealy machine. Okay? So with that definition clear, now we'll talk more about this. Next question. So let me here's an example. First of all, let me ask you this. Is this Mealy machine or Moore machine? Mealy or Moore?
Mealy.
Moore? Mealy? Or either? Or both? Moore. Moore machine, right? Because the output produces state motion. Motion, right? Transition diagrams are shown here. 4 state Q1, Q0, 1, 2, 3. And from Q1, 0, if it's A, go to Q1. If it's B, go to Q3. Same as final timer. But one more column needed because output. Q1, output is Q0, output is 1. Q1, output is 0. Q2, output is 0. Q3, 1. Additional column here, output by the order state. This is additional column. That is different from final. Final timer. If you remove this, it's same as what? Final timer. Okay? Because that one column to represent output from each state, it is. So my question now is, so here's my question. For you, see if you can, what will be the output based on input is and then output will be OPT output. It's not like CPT OPT. This OPT is output. So what would be output? Piece of paper. Please trace. Not with the eyeballs. With pencil, paper, please. Suppose. So you can trace them to get the output. Generate the output. Zero. So first you have what? 1, right? At the beginning you have 1, right? Then we get what? A. So we go 0. Because B 0. And then A 1. And A 1. And B. Okay. Here this and this. This is a extra. Because that's ignorable, but extra. So actually the output will be 1 0 0 1 1 0. Okay? Make sense? Is it accepted, not accepted? Is this string accepted, not accepted? Accepted, not accepted? Accepted, not accepted? Do you have final state?
No.
We don't have final state. No final state. So this machine is not to define any strings accepted or accepted. This string is to produce output. That's all. We don't say it's accepted or not accepted. We say the output is this. Okay? That's what we say. Is this Moore machine or Mealy machine? Moore machine or Mealy machine? Moore machine, right? So let's do one exercise. Let's trace the machine with input A, B, A, B, A, B, A, B, A, B, A, B, A. 5, 10, 15, A, B. 20. String over there is 20. And would you produce output? What did you get? One thing I see is it produces 0 all the time, except at the end, right?
Yes.
Only one stage. So when do you think it produces? Every other case you produce 0. Only one time you produce 1. When? When you have
B.
when you have
B.
from your A, B. When you have string A, B, it produces 1. When you have string A, B, do you see string A, B? Here, 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 and here, right? So that's where you produce 1. 1, 1, 1, 1. All other case what?
0.
So you count occurrences of substring A, B. Make sense? Okay? Machine. Substring A, B. Whenever substring A, B occurs, it produces. All right? Make sense? Okay, so there's no question, right? Now, next one we see is this machine. Is this Moore machine, Mealy machine? It is Mealy machine. Why is Mealy machine? Because it appears on transition. It is a transition. It is Mealy machine. Therefore, I give you this input A B A B A. A. Output please work on the example. See if you can trace the machine to produce output.
Zero one zero one 0 1 0 1.
0
It is
0 1 0 1 0.
so. It is what?
0
This A 0
1 B is
1
0
0
1 1
1
1
1.
0 1.
Is it A, right?
Yeah, 0. A by 0. From
A B
start state.
A B A B A A B 1 and then A 0
1. Q1 to Q.
0 1 0 1 1 0 0 1 0 1 1 0 1. So this is a Mealy machine. Output is produced on transition. All right, ladies, any more questions, please? Now, so we know what Mealy machine and Moore machine is, right? So it's trivial. Machine is very similar, but we know what they are. But the question now is whether they are different or same. But it said, first of all, you started like the teacher said, saying Moore machine is equal to Mealy machine. So the question is, how do you prove that two machines are the same? How would you prove it? Okay. So the way we prove is Moore machine and Mealy machine the same. The way we prove is now we do two ways. One, given Moore machine, we can build corresponding Mealy machine, and the next, given a Mealy machine, we can build corresponding Moore machine. Then we can say that Moore machine is equal to. We use this symbol because they don't look exactly the same, but they are the same machine. Given the machine defining same language, we build another machine that defines same language. So we're going to show this. First of all, theorem says this. When there is Moore machine, case one, when there is a Moore machine, you have Mealy machine, this way, right? Given a Moore machine, there's a Mealy machine. So Moore machine looks like what? Moore machine looks like you have state one and you have output, right? That's what Moore machine typically, because Moore machine produces output on each state. So if you produce output on each state, that's Moore machine. Then how do you make this Moore machine look like a Mealy machine? How? How do you produce Moore machine look like a Mealy machine? What is Mealy machine? Move machine, Mealy machine means you have to put output. Yeah, you have to put output on the transition. So how do you make output to transition? Which transition do you want to make it? So in other words, the way we do is to convert move machine to Mealy machine. State one, case 1 here is move. In other words, eliminate output from the state. However, then for example, right? But eliminate an output from the transition and move from the state, move it to transition. So that A, I need to move what here. Make sense? What about this here? You move here, right from the next state. So basically, you follow this principle, then case 1 taken care of. Every time, move the output from state to the incoming edges. Everything. Is it clear? So move from the state to incoming edges. Okay? For example, here. Oh, here's it explained. So T is moved from Q state, Q4 to next, to the incoming edges, right? Now, here's what I'd like you to do. I'd like you to, as an exercise, let's make this little, let's make it tandem. Do you see this? What machine is this? Move machine, right? Can you convert this to Mealy machine? Give me 2 minutes. Can you convert this to Mealy machine? Move this move machine to Mealy machine. Yes, I think so. We can. You see, same. So I have to move. Once inside of a state, you move it to the incoming, right? This one you don't have any, but nothing to do. Just remove it. Okay. So that's how we convert move machine to Milling machine. Second case is to milling machine to vacuum machine. Here, when you have milling machine, then you have move machine. Milling machine means you have output and transition, right? Output and transition. For example, here's an example. So you have this as milling machine, right? Now how do I move this output from transition to the state? That's the question. How do you move those the output of the transition to the state?
The transition from output goes into
Transition goes into the
output transition.
up,
The output transition.
incoming. That is incoming. Incoming first. So when you do incoming transitions, incoming transitions. How would you do that? So we only look at this case income. How many incoming edges? 3. Output. How many output headers?
2.
How many output headers? 2. They are 0 and 1. How many output can go into the state? How many output can go into the state?
Only one.
1. How many output headers do you have to have? 2. How many output in the state? 1. So how many states do you need? You have 2, right? You need 2 output, not 1. You need to have 2. Okay? So you need to have Q4 slash 0, Q4 slash 0, and these 2, right? And then another one, Q4 prime, okay, slash 0. You have to have a two identical state of Q4. We call it twin, okay? Q4 prime and Q4 double prime slash 1. You have 1. Q4 double prime slash 1 is B edges. And Q4 single prime slash 0, you have 2 incoming. So there are 2 states. And both states have same number of outgoing. So let me show you. Q4 prime 0, 2, right? AB. Q4 double prime 1, there's 1, and 2 outgoing is this way. Do you see? Do you see? So you need to have 2 states. The one producing 1, the other one producing 0, but those 2 are the ones that produce 0, right? Those 2, this is one that produces 1. Now, they are both Q4 and Q4. However, we put 1 prime, 2 primes because to distinguish the twin, however. Okay? The twin, same Q4. And the outgoing edges are no change. A1, B1, A1, B1. Because those are taken care of by next state. Make sense? Does that make sense? Now let me ask you this question here. How about this? Can you work on this? Is this milling machine, right? Please convert this into more machine. It's okay. That's right. I'm just reminding you. So how many incoming edges? 2. How many output?
1, 2. 2 to
0, 2. So you have to have 2, right? 2 Q3s.
Yes.
1 for 0, 1 for?
1, 1.
Okay. So, and 0 comes this way. 1 is self to self. So you'll have Q3, 0 and Q3, 1, right? Outgoing are same. There's a Q6, 0, A, but now this will be A, right? And then B. However, they are the same, right? Self to self is same. B, right? Same. Q3 prime and double prime, same, twin. So self to self. So that's basically after you convert Mealy machine to more. Do you see how it looks? Make sense? Do you agree with this? Is it understandable? How it works? Because this case, again, like I said, 0, that's okay. 1, that's okay. However, this thing is, that is, I'm sorry, the same, it's basically, this one is for 1, but that is needed. But they are the same. It's like self to self, same. This one is the same, right? They're the same. And then, whatever produces 0 are connected to this. So therefore, 1 is true, 2 is true, therefore we say Moore machine and Mealy machine, they are identical. The one exercise here that I'd like you to do is, let's work on this problem. This is a Mealy machine, right? Can you convert it to Moore machine? Exercise. Moore machine to Mealy machine to Moore machine, please. The way we do is, how many state Q0 do you need? Two, right? You don't know. How many Q1 do you need?
One.
Only one. So 2, 1, and then how many?
Two.
Two, right? Two. You need two of Q2, two of Q1, one. How many do you need?
One.
0, right? So 1, 2, 3, 4, 5, 6. Draw the 6th state first, and then start building. Okay? So when you have 6 state, start building it. You'll come up with the following. Here is the answer. Wow, it looks so simple. Once you build the 6, so 2, and then 2, and 1, 1, right? Then you start connecting it. That's how we do. So the 6 state, connect, and that's the final Moore machine that's floating from the conversion process. Make sense? So, all right. So, next, basically, I think that's it. So in this chapter, we talked about two machines that produces output string in response to input string, right? Produce output string in response to input string. The machines that produce output on the state are called, if they produce output on the state, Moore machine. If they produce output on the transition, Mealy machine. Given a Mealy machine, we can build Moore machine corresponding to it. Given a Moore machine, we can build Mealy machine that corresponds to it. So we can conclude that Moore machine is equivalent to probably there'll be on the exam problems on the exam on converting Moore machine to or Mealy machine or to Moore machine. Okay, so you need to exercise. So exercise problems I'd like to give you at the end of the chapter are page 165, problems 3.4 and 5. Problem 3.4 and 5, convert Moore machine to Mealy machine. And 6.3 and 4, 6.3 and 4, convert Mealy machine to Moore machine. Okay? Okay? Those two problems. That makes sense? So today we covered Moore machine, Mealy machine, and then we covered transition graph. And we covered non-deterministic nature, right? Non-deterministic. And transition graph. We covered Moore machine, Mealy machine. Next time, what we're going to cover, chapter 7. Chapter 7. How many pages? Chapter 7. Mealy theorem. Mealy theorem. Chapter 7 is about 50 pages. Now I'm going to show you my way. I'm going to summarize those and show you chapter 7 and potentially 7 and probably 7 and 9, okay? So we'll talk about those next week, okay? But I'd like to suggest that you complete the homework side. Don't have to turn in, but do this. And then all those example problems in the chapters, we should do. That way, stay fresh. Okay? We'll meet next time and do this, okay?